There's something in the night sky racing toward us at 400,000 kilometers per hour. You can see it with your naked eye on a clear evening, a faint smudge in Andromeda that most people ignore. But that innocent patch of light contains 1 trillion stars, and in 4 billion years, it's going to collide with our galaxy in the most spectacular cosmic event imaginable. Today, we're going to witness the final hour of this cosmic dance, explore what science tells us about galaxy collisions, and discover why this seemingly catastrophic event might actually be the beginning of something beautiful. Before we begin this journey, let me know in the comments below from where in the world you are watching from and what hour it is. It's always fun to know where our viewers are watching from. Now let's begin. The Andromeda Galaxy, also known as Messier 31 or M31, is our nearest major galactic neighbor. At 2.5 million light-years away, it's the most distant object visible to the naked eye. When you see it in the sky, you're looking at light that left Andromeda when our ancestors were just beginning to use stone tools. That light has been traveling through the cosmic void for longer than our species has existed, and it carries within it the story of a galaxy that will one day merge with our own. Edwin Hubble first confirmed that Andromeda was a separate galaxy beyond our Milky Way in 1925, revolutionizing our understanding of the universe's scale. Before his observations, many astronomers believed the Milky Way was the entire universe. Hubble's discovery using Cepheid variable stars as distance markers revealed that Andromeda was an island universe of its own, similar to but larger than our galaxy. This finding expanded our cosmic perspective overnight, transforming humanity's place in the universe from residents of the only galaxy to inhabitants of one among countless billions. But Andromeda held another surprise. While Hubble found that most galaxies were moving away from us due to cosmic expansion, Andromeda was different. It was moving toward us. Astronomers initially thought this might be a measurement error, but repeated observations confirmed it. Andromeda and the Milky Way are on a collision course. The blue shift in Andromeda's light spectrum tells us it's approaching at roughly 110 kilometers per second, though recent measurements from the Gaia Space Telescope have refined this value with unprecedented precision. The Hubble Space Telescope conducted a groundbreaking study between 2002 and 2010, tracking the tiny movements of stars within Andromeda to determine not just its approach speed, but also its sideways motion. This was like watching individual grains of sand move on a beach from an airplane, an incredibly delicate measurement that pushed our instruments to their limits. The results confirmed what many had suspected. This isn't going to be a glancing blow or a near miss. Andromeda and the Milky Way are headed for a direct hit. Let's put this cosmic collision in perspective. The Milky Way spans about 100,000 light-years in diameter and contains between 200 and 400 billion stars. Andromeda is even larger, stretching roughly 220,000 light-years across, with approximately 1 trillion stars. Both galaxies are surrounded by halos of dark matter extending far beyond their visible boundaries, making their total masses roughly comparable despite Andromeda having more stars. These aren't just random collections of stars floating through space. Both galaxies are intricate systems with spiral arms, central bulges, and supermassive black holes at their hearts. The Milky Way's central black hole, Sagittarius A star, weighs in at 4 million solar masses. Andromeda's central black hole is even more massive, estimated at 100 million solar masses. When these galaxies merge, these black holes will eventually find each other in one of the universe's most violent events. But let's talk about what collision really means in the context of galaxies. Space is vast and stars are tiny compared to the distances between them. In our solar neighborhood, the average distance between stars is about 4 light-years. To put that in perspective, if the Sun were the size of a golf ball, the nearest star would be another golf ball about 750 kilometers away. Even in the densest star clusters, collisions between individual stars are extraordinarily rare. This spacing means that when Andromeda and the Milky Way collide, they'll actually pass through each other like two clouds merging. The stars will weave between each other, their gravitational fields interacting and disrupting orderly orbits, but direct stellar collisions will be almost non-existent. Computer simulations suggest that over the entire merger process, which will take billions of years, perhaps only a handful of stars might actually collide, out of more than 1 trillion total. The real drama happens through gravitational interactions. As the galaxies approach, their mutual gravity will begin distorting their shapes. Spiral arms will stretch and warp, creating spectacular tidal tails that extend for hundreds of thousands of light years. Stars will be flung into wild new orbits. Some will be ejected from their galaxies entirely, doomed to wander intergalactic space forever. Others will plunge toward the galactic centers, feeding the supermassive black holes and potentially triggering brilliant quasar activity. NASA's computer simulations, particularly those created by astronomers Frank Summers and Gertina Besler, show this cosmic ballet in stunning detail. They've modeled billions of individual star particles, tracking their movements over billions of years as the galaxies approach, collide, separate, and collide again before finally settling into a single, massive, elliptical galaxy. These simulations require supercomputers running for months, solving gravitational equations for countless interacting bodies. The visualizations they produce are both scientifically accurate and breathtakingly beautiful, showing streams of stars flowing between the galaxies like cosmic rivers. The European Space Agency's Gaia mission has revolutionized our understanding of both galaxies' structures and movements. Launched in 2013, Gaia has mapped over 1 billion stars in our galaxy with unprecedented precision, measuring their positions and velocities to create the most detailed three-dimensional map of the Milky Way ever produced. This data has revealed that our galaxy has already survived previous collisions. The Sagittarius dwarf galaxy is being torn apart and absorbed by the Milky Way right now, and Gaia has traced streams of stars from this dying galaxy wrapping around our own like ribbons. And if this cosmic collision is fascinating you as much as it fascinates me, hit that subscribe button and give this video a thumbs up. Your support helps these universe-shattering discoveries reach more curious minds like yours. Trust me, what's coming next will change how you see the night sky forever. These smaller collisions are previews of the main event. The Milky Way has consumed dozens of smaller galaxies over its lifetime, growing larger with each merger. Andromeda has done the same. In fact, recent studies suggest Andromeda experienced a major merger with another large galaxy about 2 billion years ago, which might explain its slightly disturbed structure and the double nucleus at its center. We're not witnessing two pristine galaxies meeting for the first time. We're watching battle-scarred veterans preparing for their ultimate confrontation. Speaking of rare cosmic events, galactic collisions of this magnitude are extraordinarily uncommon in our local universe today. While they were more frequent in the early cosmos when galaxies were closer together, major mergers between spiral galaxies have become increasingly scarce. If you're fascinated by cosmic rarities, you might enjoy my video on the rarest objects in the universe, where I explore phenomena even more unusual than galactic collisions, things that shouldn't exist according to conventional physics. The link is in the description and pinned on the comments. But let's return to our impending cosmic merger. The timeline of this collision stretches our imagination. 4 billion years from now, Andromeda will loom large in our night sky, appearing 6 times the size of the full moon. Its spiral structure will be clearly visible to the naked eye, a constant reminder of the approaching merger. The night sky will be transformed into something alien and spectacular. Imagine looking up and seeing another galaxy's spiral arms stretching across the heavens, its individual star-forming regions visible as glowing patches of light. By 3.75 billion years from now, the first close approach will begin. The galaxies won't merge immediately, but will swing past each other in a cosmic gravitational dance. Tidal forces will pull streams of stars and gas from both galaxies, creating spectacular bridges and tails visible from any planets that might exist. Star formation will accelerate dramatically as gas clouds compress, triggering a galactic starburst. The sky will be filled with brilliant young star clusters and glowing nebulae. The two galaxies will separate after this first pass, but they're now gravitationally bound. They'll swing back together for a second collision about 4.5 billion years from now. This cosmic dance will repeat several times, with each pass bringing the galactic cores closer together. The spiral structures will be completely destroyed, replaced by chaotic streams of stars following wild, looping orbits. During this period, our Sun will be experiencing its own dramatic changes. In about 5 billion years, it will exhaust its hydrogen fuel and begin expanding into a red giant star. Earth will likely be consumed or at least rendered completely uninhabitable. If humanity or our descendants still exist, we'll need to have migrated to other star systems long before the galactic collision reaches its climax. The merger with Andromeda might actually help in this regard, as the gravitational disruptions could send our solar system into a higher orbit, potentially extending the habitable period. Computer models suggest our solar system has about a 12% chance of being ejected from the merged galaxy entirely during one of the collision passes. We could become residents of intergalactic space, watching the merger continue from a distance of hundreds of thousands of light years. The night sky from such a vantage point would be extraordinary. The merged galaxy would appear as a brilliant cloud of light, slowly evolving over millions of years. The fate of stars during the merger depends largely on their location within their original galaxies. Stars in the outer regions of galactic disks are most likely to be flung into extended orbits or ejected entirely. Stars closer to the galactic centers will tend to remain bound, but will have their orbits dramatically altered. The orderly rotation of spiral arms will be replaced by random, elliptical orbits characteristic of elliptical galaxies. New star formation will surge during the merger. When galaxies collide, their gas clouds, which make up about 10 to 15% of a galaxy's normal matter, collide too. Unlike stars, gas clouds are extended objects that can't pass through each other without interacting. They compress, heat up, and trigger massive bursts of star formation. These starburst events can increase a galaxy's star formation rate by factors of hundreds or thousands. The James Webb Space Telescope has observed similar galaxy mergers in the distant universe, providing real examples of what our collision might look like. The antennae galaxies, located about 45 million light-years away, show two spiral galaxies in the midst of their merger. Long tidal tails stretch away from the colliding pair, and intense star formation creates brilliant blue clusters throughout the disturbed regions. The Cartwheel Galaxy shows the aftermath of a smaller galaxy punching through a larger one, creating ripples of star formation spreading outward like waves on a pond. These observations from the James Webb Space Telescope aren't just pretty pictures, they're time machines showing us our own future. When we observe the Mice galaxies NGC 4676, we're seeing two galaxies about 160 million years after their first approach, with long tidal tails stretching over 300,000 light-years. This could be the Milky Way and Andromeda several hundred million years after our first close encounter. The distorted shapes, the streams of stars connecting the galaxies, the bright knots of new star formation, all of this awaits our cosmic neighborhood. But perhaps the most dramatic event in this entire merger will be the collision of the supermassive black holes at each galaxy's heart. This won't happen quickly. For billions of years after the galaxies begin merging, the black holes will orbit each other at distances of thousands of light years. Dynamical friction, a process where the black holes transfer energy to surrounding stars, will gradually bring them closer together. Stars passing near the black holes will be accelerated and flung outward, carrying away orbital energy and causing the black holes to spiral inward. When the black holes finally get within a few light years of each other, they'll form a binary system. This is where things get really interesting. A binary supermassive black hole system can clear out the stars from the galactic center, creating a relatively empty region several light years across. Any star that ventures too close will be ejected at tremendous speeds. Some might even become hypervelocity stars, shot out of the galaxy at speeds exceeding 1,000 kilometers per second. The final parsec problem has puzzled astronomers for decades. Models suggest that when supermassive black holes get within about a parsec, 3.26 light-years of each other, the mechanisms that brought them together become less efficient. There might not be enough stars left in the central region to carry away their orbital energy through gravitational interactions. How do they bridge this final gap? The answer might involve gas dynamics, triple black hole interactions if a third galaxy is involved, or gravitational wave radiation. Once the black holes get close enough, within a few hundredths of a parsec, gravitational wave emission takes over. They'll radiate away their orbital energy as ripples in space-time itself, spiraling together faster and faster. In the final moments before merger, they'll be orbiting each other hundreds of times per second, warping space and time in their vicinity beyond recognition. The gravitational waves produced will be far more powerful than anything LIGO has detected from stellar mass black hole mergers. The Laser Interferometer Space Antenna, or LISA, scheduled for launch in the 2030s, will be capable of detecting gravitational waves from merging supermassive black holes throughout the observable universe. When the Milky Way and Andromeda's black holes finally merge, billions of years from now, any gravitational wave detectors in distant galaxies would observe one of the strongest signals in their sky. The merger will release more energy in gravitational waves than all the stars in both galaxies produce in light over millions of years. After the black holes merge, the resulting monster will weigh about 104 million solar masses. The combined mass of both original black holes minus a small amount radiated away as gravitational waves. This new black hole might receive a gravitational wave recoil kick, potentially launching it out of the galactic center at speeds of thousands of kilometers per second. Such a recoiling black hole would oscillate through the merged galaxy for millions of years before friction with surrounding stars and gas brings it back to rest at the center. But what about life in this chaotic future? Could any civilization survive such a dramatic event? The answer might surprise you. Despite the violence of the merger on galactic scales, individual solar systems would likely remain intact. The distances between stars are so vast that the gravitational influence of passing stars would rarely be strong enough to disrupt planetary orbits. A planet like Earth, if it still existed and remained habitable, would continue orbiting its star much as before. The main threat to life would come from increased radiation. The starburst triggered by the collision would produce numerous massive stars that live fast and die young, exploding as supernovae. The rate of supernovae in the merging galaxy could increase by factors of 10 to 100. If a supernova occurred within about 30 light-years of an inhabited planet, the radiation could damage its ozone layer and trigger mass extinctions. The gamma-ray bursts from the most massive stellar explosions could be lethal at even greater distances. However, the merger might also create new opportunities for life. The burst of star formation will create billions of new solar systems, potentially including many habitable planets. Elements essential for life, carbon, oxygen, nitrogen, and others, will be distributed throughout the merged galaxy by stellar winds and supernova explosions. The merger could actually seed the conditions for life to flourish in places where it couldn't exist before. The Spitzer Space Telescope, before its retirement in 2020, studied numerous galaxy mergers in infrared light, revealing hidden details about star formation and galactic structure. These observations showed that merger-triggered starbursts tend to be concentrated in the galactic centers and in the regions where gas clouds collide most violently. The infrared light penetrates dust that blocks visible light, showing us stellar nurseries that would otherwise remain hidden. Current estimates suggest that the merger will produce about 600 billion new stars over the course of several billion years. That's more than the current number of stars in the Milky Way. Most of these will be red dwarfs, small, cool stars that can shine for trillions of years. But there will also be massive blue giants, sun-like stars with planetary systems, and everything in between. It's a cosmic baby boom on an almost incomprehensible scale. The distribution of dark matter during the merger adds another layer of complexity to this cosmic event. Dark matter makes up about 85% of each galaxy's total mass, forming enormous halos that extend far beyond the visible stars. When Andromeda and the Milky Way collide, their dark matter halos will merge first, beginning to interact when the galaxies are still millions of light-years apart. This invisible collision will set the stage for everything that follows. Simulations by the Illustris project, one of the most sophisticated cosmological simulations ever created, show how dark matter behaves during galaxy mergers. Unlike normal matter, dark matter doesn't experience friction or pressure. It only interacts gravitationally, passing through itself like a ghost. The dark matter halos will merge smoothly, creating a combined halo that will eventually settle into a roughly spherical shape around the merged galaxy. This dark matter merger will affect the visible matter in subtle but important ways. The gravitational field of the combined dark matter halo will determine the final structure of the merged galaxy. Stars and gas will settle into orbits determined by this invisible mass distribution. The dark matter will act like an invisible skeleton, providing the gravitational framework that shapes the visible galaxy. Recent observations from the Chandra X-ray Observatory have revealed what happens to hot gas during galaxy collisions. The space between stars in galaxies isn't empty, it contains thin, hot gas heated to millions of degrees. When galaxies collide, this gas experiences ram pressure, compression, and shock heating. The Bullet Cluster, a famous example of colliding galaxy clusters, shows how gas can be separated from dark matter during collisions, with the hot gas lagging behind the dark matter and galaxies. In the Milky Way Andromeda merger, the hot gas will be compressed and heated to even higher temperatures, emitting X-rays that future telescopes could observe from distant galaxies. This gas will eventually cool and fall toward the center of the merged galaxy, potentially feeding the central black hole and triggering periods of active galactic nucleus activity. The merged galaxy might even briefly become a quasar, with the central black hole shining brighter than all the stars combined. Let's zoom in on what this merger means for specific objects we know and love. The Orion Nebula, that stellar nursery visible to the naked eye, will likely be disrupted and dispersed long before the merger completes. The Pleiades star cluster might be torn apart by tidal forces or could survive intact, but in a completely different orbit. The globular clusters that orbit both galaxies, ancient, dense collections of hundreds of thousands of stars, will mostly survive the merger, though their orbits will be dramatically altered. Speaking of globular clusters, they provide clues about previous galactic mergers. Many of the Milky Way's 150 known globular clusters show chemical compositions suggesting they originally formed in other galaxies that our galaxy consumed. Omega Centauri, the largest globular cluster visible from Earth, might actually be the stripped core of a dwarf galaxy that the Milky Way absorbed billions of years ago. After the Andromeda merger, the combined galaxy will have around 400 globular clusters, a fossil record of its violent assembly. The merger will also affect the satellite galaxies that orbit both the Milky Way and Andromeda. The Milky Way has at least 59 known satellite galaxies, including the large and small Magellanic Clouds visible from the southern hemisphere. Andromeda has a similar collection of satellites. During the merger, many of these smaller galaxies will be stripped away or absorbed. Some might be exchanged between the main galaxies like cosmic trading cards. Others might be flung into intergalactic space, becoming orphaned galaxies, drifting alone through the cosmic void. The Triangulum galaxy, also known as M33, deserves special mention. This beautiful spiral galaxy is the third largest member of our local group after Andromeda and the Milky Way. Located about 2.7 million light-years away, Triangulum might play a supporting role in the upcoming merger. Some models suggest it could collide with the Milky Way first, about 2 billion years before the main Andromeda collision. Other simulations show it participating in the merger as a third partner, creating an even more complex gravitational dance. Current observations from ground-based telescopes using adaptive optics have revealed stunning details about Andromeda's structure that will affect the merger dynamics. Andromeda appears to have a double nucleus, either two supermassive black holes orbiting each other or a single black hole surrounded by an eccentric disk of old stars. This unusual central structure might be evidence of a previous major merger in Andromeda's past, suggesting our neighbor galaxy is no stranger to cosmic collisions. The Very Large Array Radio Telescope in New Mexico has mapped the neutral hydrogen gas in both galaxies, revealing extended gas disks that stretch far beyond the visible stars. This gas will be the first component to interact as the galaxies approach, potentially triggering star formation even before the main collision begins. Radio observations also show that both galaxies are already exchanging gas through a faint bridge of material. The collision has already begun in this sense. The chemical evolution of the merged galaxy will be fascinating to track. Right now, the Milky Way and Andromeda have slightly different chemical compositions. Andromeda appears to be more metal-rich, meaning it has a higher proportion of elements heavier than hydrogen and helium. When the galaxies merge, these different stellar populations will mix, creating a galaxy with a complex chemical history written in the spectra of its stars. Stellar archaeologists study these chemical signatures today using spectrographs on major telescopes like Keck, Gemini, and the Very Large Telescope. Each star carries within it the chemical fingerprint of the gas cloud from which it formed. By analyzing thousands of stars, astronomers can reconstruct the history of our galaxy's assembly. The Apogee survey, part of the Sloan Digital Sky Survey, has analyzed the chemistry of hundreds of thousands of Milky Way stars, revealing that our galaxy's thick disk formed from a major merger about 10 billion years ago. The merged Milky Way Andromeda Galaxy will eventually have similarly complex chemistry, telling the story of our collision. The final merged galaxy has already been given names by imaginative astronomers. Some call it Milkomeda, others prefer Milkdromeda, and a few have suggested the simple but elegant Andro-Milk. Whatever we call it, this galaxy will be dramatically different from either parent. The beautiful spiral arms will be gone, replaced by a smooth, featureless elliptical or spheroidal shape. Instead of orderly rotation, stars will follow random, elongated orbits in all directions. The galaxy will be larger but less structured, a cosmic retirement home where little new star formation occurs. Elliptical galaxies are sometimes called red and dead because they contain mostly old red stars and little gas for making new ones. The merger process will be remarkably efficient at consuming or expelling the gas that fuels star formation. The initial starburst will convert much of the available gas into stars. Supernova explosions and radiation from young massive stars will heat and blow away additional gas. The merger process itself can eject gas through gravitational interactions. By the time the merger settles down, Milky Way might retain only a fraction of its original gas content. This transformation from spiral to elliptical represents a fundamental change in galactic personality. Spiral galaxies like the Milky Way and Andromeda are dynamic, actively forming stars, constantly evolving. Elliptical galaxies are more static, their stellar populations aging quietly without significant renewal. It's like watching a vibrant city slowly transform into a peaceful retirement community over billions of years. The supermassive black hole at the center of Milky Way will be one of the largest in the local universe. After the gravitational wave recoil from the merger settles, this monster will sit at the heart of the new galaxy, occasionally feeding on gas and stars that wander too close. Most of the time, it will be quiescent, invisible except for its gravitational effects on nearby stars, but occasionally, a star will pass too close and be torn apart by tidal forces in what astronomers call a tidal disruption event. Tidal disruption events create spectacular flares visible across cosmic distances. The star is stretched into a long strand of material that spirals around the black hole, forming a temporary accretion disk that outshines the entire galaxy. The Zwicky Transient Facility and other survey telescopes detect dozens of these events each year in distant galaxies. Milky Way's massive central black hole will produce particularly dramatic tidal disruption events, briefly illuminating the merged galaxy with the fury of a feeding supermassive black hole. What would the night sky look like from a planet in Milky Way? The answer depends enormously on where in the galaxy that planet is located. A planet near the center would see a dense, brilliant band of stars across the sky, far more spectacular than the Milky Way we see today. Stars would be so numerous and close that true darkness might never occur. A planet in the outer regions would see fewer stars, but the central bulge of the galaxy would dominate the sky as a brilliant, elongated glow. The absence of spiral structure would be the most noticeable difference from our current view. We're used to seeing the Milky Way as a band across the sky because we're looking along the disk of our spiral galaxy. In an elliptical galaxy, stars are distributed more uniformly in 3 dimensions. The view would be more symmetrical, perhaps more beautiful in its own way, but definitely alien to our eyes. One of the most poetic aspects of this merger is that we won't be here to see it. Not just humanity, Earth itself will be transformed or destroyed before the main collision begins. Our Sun will expand into a red giant in about 5 billion years, likely swallowing Mercury and Venus and scorching Earth beyond recognition. Yet this cosmic inevitability carries an important message about our place in the universe. We exist in a brief window of cosmic time when conditions are perfect for life like ours. Our Sun is stable, our planet is habitable, and our galaxy is relatively peaceful. But nothing lasts forever in the cosmos. Stars are born and die, galaxies collide and merge, and even the universe itself is evolving toward a cold, dark future. Understanding this context doesn't diminish our significance. It highlights how precious and remarkable our existence truly is. The Andromeda collision also reminds us that the universe is not static. Ancient astronomers thought the heavens were fixed and eternal, but we now know that everything is in motion, everything is changing. The constellations we see tonight are different from what our ancestors saw, and they'll be different still for our descendants. The Milky Way we call home is just one snapshot in a long movie of cosmic evolution. Now, if you're still with me at this point in the video, I want to take a quick moment to thank you. We've journeyed through billions of years of cosmic evolution together, from the approaching collision to the final merged galaxy. If you're finding this exploration of our galactic future as fascinating as I do, consider subscribing to the channel. I explore these cosmic mysteries regularly, and having you along for the ride means more than you know. All right, let's continue our journey. Astronomers use the local group, the collection of galaxies including the Milky Way, Andromeda, Triangulum, and about 80 smaller galaxies, as a laboratory for understanding galaxy evolution. We can study these nearby galaxies in exquisite detail, measuring individual star properties, mapping gas distributions, and tracking stellar motions that would be impossible to observe in more distant galaxy groups. The local group is gravitationally bound, meaning its member galaxies won't be separated by cosmic expansion. While distant galaxy clusters are receding from us at ever-increasing speeds, the local group will remain together, slowly merging over the next several billion years. Milky Way will eventually absorb most of the smaller satellite galaxies, growing even larger. Triangulum, if it survives as a separate entity through the main merger, will eventually fall in too. The dynamics of this cosmic collision become even more fascinating when we consider the role of magnetic fields. Both the Milky Way and Andromeda possess complex magnetic field structures that thread through their spiral arms and extend into their halos. These magnetic fields, though incredibly weak by terrestrial standards, play crucial roles in star formation and the behavior of interstellar gas. When the galaxies collide, their magnetic fields will interact in ways we're only beginning to understand. Radio telescopes like the Very Large Array and the upcoming Square Kilometre Array can map these magnetic fields by observing polarized radio emission from cosmic ray electrons spiraling around magnetic field lines. Current observations show that galactic magnetic fields are surprisingly well organized, following the spiral arm structure and extending far beyond the visible galaxy. During the merger, these ordered fields will become tangled and amplified, potentially affecting how gas flows and where new stars form. The collision will also trigger phenomena we rarely see in isolated galaxies. Shock waves will propagate through the interstellar medium as gas clouds collide at hundreds of kilometers per second. These shocks will heat gas to millions of degrees, creating vast bubbles of hot plasma that emit X-rays. The Chandra X-ray Observatory has observed similar shock-heated gas in other galaxy mergers, revealing temperatures exceeding 10 million Kelvin, hot enough to strip electrons from iron atoms. Computer simulations by the FIRE collaboration have revealed surprising details about how gas behaves during galaxy mergers. Unlike the smooth, predictable motions of stars, gas dynamics are chaotic and turbulent. Gas clouds can be compressed to trigger star formation in one region while being heated and dispersed in another. The simulations show that merger-driven turbulence can persist for billions of years after the initial collision, continuing to influence star formation long after the galaxies have settled into their final configuration. The cosmic ray population will also be dramatically affected. Cosmic rays are high-energy particles accelerated by supernova shockwaves and other violent processes. During the merger, the increased supernova rate will boost cosmic ray production, while the tangled magnetic fields will trap these particles more efficiently. The merged galaxy might glow brighter in gamma rays produced by cosmic ray interactions with interstellar gas. One of the most intriguing aspects of the collision involves the fate of stellar streams. Long, thin trails of stars torn from disrupted star clusters and satellite galaxies. The Milky Way already contains numerous stellar streams discovered by surveys like the Dark Energy Survey and the Gaia mission. These streams are like fossil records, preserving information about past galactic interactions. During the Andromeda merger, existing streams will be disrupted and new ones created, writing a complex history in the positions and motions of stars. The Sagittarius stream, created by the ongoing destruction of the Sagittarius dwarf galaxy, currently wraps around our galaxy multiple times like ribbons around a present. When Andromeda arrives, the gravitational chaos will shred this stream and scatter its stars throughout the merged galaxy. Future galactic archaeologists will need sophisticated computer models to untangle this stellar spaghetti and reconstruct the merger history. Hypervelocity stars represent another fascinating consequence of galactic interactions. These are stars moving so fast they can escape the galaxy entirely, traveling at speeds exceeding 500 kilometers per second. The Hills mechanism, proposed by astronomer Jack Hills, suggests these stars are created when binary star systems pass close to a supermassive black hole. One star is captured while the other is flung away at tremendous speed. During the merger, the chaotic gravitational environment will create many more hypervelocity stars, some potentially reaching speeds of several thousand kilometers per second. The Gaia mission has already discovered dozens of hypervelocity stars in our galaxy, including some that appear to have originated in Andromeda. These stellar refugees might be advanced scouts of the coming collision, stars ejected from Andromeda by previous interactions with smaller galaxies. By studying their chemical compositions and ages, astronomers can learn about conditions in Andromeda billions of years ago. Pulsar timing arrays offer another window into the merger's effects. Pulsars are rapidly spinning neutron stars that emit beams of radio waves like cosmic lighthouses. Their rotation is so stable that they rival atomic clocks in precision. When gravitational waves pass through space, they slightly change the distances between Earth and distant pulsars, creating detectable timing variations. The North American Nanohertz Observatory for Gravitational Waves and similar projects are already detecting gravitational wave backgrounds from supermassive black hole mergers throughout the universe. As Andromeda approaches, the gravitational wave signals will strengthen. Decades before the galaxies actually collide, sensitive pulsar timing arrays might detect the orbital motion of the two galaxies around their common center of mass. This would provide unprecedented insights into the dark matter distributions and total masses of both galaxies. The gravitational wave astronomy of the future will transform our understanding of cosmic collisions. The merger will also affect the circumgalactic medium, the hot, diffuse gas that surrounds galaxies in halos extending hundreds of thousands of light years. This gas, heated to millions of degrees by supernova explosions and stellar winds, contains more mass than all the stars in the galaxy. When Andromeda and the Milky Way collide, their circumgalactic media will merge first, creating shock waves and turbulence that will influence the subsequent evolution of both galaxies. Recent observations with the Hubble Space Telescope's Cosmic Origin spectrograph have mapped the circumgalactic medium around nearby galaxies by studying how it absorbs light from background quasars. These observations reveal a complex ecosystem of gas flows, with material constantly cycling between the galaxy and its surrounding halo. The merger will disrupt these flows, potentially starving the merged galaxy of the gas needed for continued star formation. The role of stellar feedback becomes crucial during the merger. When massive stars explode as supernovae, they inject enormous amounts of energy into their surroundings, heating gas and driving powerful winds. During the starburst phase of the merger, this feedback will be amplified dramatically. Simulations suggest that stellar feedback could blow away most of the remaining gas, effectively ending star formation and transforming the merged galaxy into a red and dead elliptical. But stellar feedback isn't just destructive, it's also creative. Supernova explosions enrich the interstellar medium with heavy elements forged in stellar cores. Carbon, oxygen, silicon, iron, and dozens of other elements essential for planet formation and life are scattered through space by dying stars. The merger will accelerate this chemical enrichment, distributing metals throughout the merged galaxy and setting the stage for future generations of planets and potentially life. The infrared emission from the merged galaxy will be spectacular. Dust grains in star-forming regions absorb ultraviolet and visible light from young stars and re-emit it at infrared wavelengths. The James Webb Space Telescope and future infrared observatories will be able to study similar mergers in the distant universe, seeing through the dust to observe star formation in unprecedented detail. These observations provide templates for understanding our own galactic future. Galaxy mergers like the one awaiting us are cosmic recycling centers. They take two mature spiral galaxies and transform them into something entirely different. The process destroys the original structures but creates new ones. It's a reminder that destruction and creation are intimately linked in the universe. Every ending enables a new beginning. The gravitational wave signature of our merger will be unlike anything we've detected so far. Current gravitational wave observatories like LIGO and Virgo detect waves from stellar mass black holes and neutron stars merging in fractions of a second, but supermassive black hole mergers unfold over millions of years, producing gravitational waves at much lower frequencies that require space-based detectors to observe. The Laser Interferometer Space Antenna, scheduled for launch in the 2030s, will open this new window on the universe. LISA will consist of 3 spacecraft flying in formation 5 million kilometers apart, using laser interferometry to detect the stretching and squeezing of space itself. When our galactic black holes finally merge, billions of years from now, LISA's descendants will observe gravitational waves that carry information about the masses, spins, and orbital dynamics of these cosmic monsters. But LISA will do more than just detect the merger. It will provide early warning. Supermassive black hole binaries emit gravitational waves for millions of years before their final coalescence. Future gravitational wave observatories will be able to track these systems as they spiral together, predicting exactly when and how they'll merge. It's like having a cosmic calendar that tells you when the most violent events in the universe will occur. The electromagnetic counterparts to supermassive black hole mergers remain largely theoretical, but they could be spectacular. As the black holes spiral together, they'll disrupt any accretion disks around them, potentially triggering brilliant flares visible across cosmic distances. The final merger might produce jets of high-energy particles that could outshine entire galaxies for brief periods. Future telescopes will search for these electromagnetic signatures to complement gravitational wave observations. The merger will also create what astronomers call a galactic fossil group. Most galaxies today exist in groups or clusters containing dozens to thousands of members, but over cosmic time, the largest galaxy in each group tends to cannibalize its smaller neighbors through gravitational interactions. Eventually, only one giant elliptical galaxy remains, surrounded by a sparse population of globular clusters and planetary nebulae, the fossils of its former companions. Milky Way will likely become such a fossil group, having absorbed most of the local group's smaller galaxies. The Magellanic Clouds currently orbiting the Milky Way will probably be consumed during the merger process. The dozens of dwarf galaxies that currently orbit both the Milky Way and Andromeda will either be accreted or flung into intergalactic space. In 10 billion years, Milky Way might be the only significant galaxy within tens of millions of light-years. This galactic loneliness will have profound implications for any civilizations that might exist in the far future. Today we can study nearby galaxies to understand cosmic evolution and test our theories of physics, but future astronomers in Milky will see a much emptier universe. The cosmic expansion driven by dark energy will have carried distant galaxies beyond the observable horizon, while nearby galaxies will have been absorbed. The universe will appear static and eternal to these future observers, much as it did to astronomers before Hubble discovered cosmic expansion. The concept of cosmic horizons becomes crucial here. We're living in a special epoch when the universe's expansion history is still visible in the cosmic microwave background and the distribution of galaxies. But dark energy is accelerating the expansion, eventually carrying all but the nearest galaxies beyond our ability to observe them. Future civilizations will inherit a universe that appears fundamentally different from the one we see today. This connects to a deeper philosophical point about our place in cosmic history. We exist during a brief window when the universe is old enough for complex life to evolve, but young enough that evidence of the Big Bang and cosmic evolution remains visible. It's a cosmic Goldilocks zone in time, not too early, when the universe was too hot and chaotic for stable structures, and not too late, when the evidence of cosmic evolution will have disappeared beyond the horizon. The merger will also affect the local group's escape velocity, the speed needed to leave the gravitational influence of our galactic neighborhood. Currently, this velocity is about 550 kilometers per second. After the merger, Milky's increased mass will raise the escape velocity significantly. Any spacecraft launched from the merged galaxy will need more energy to reach intergalactic space, making interstellar and intergalactic travel even more challenging for future civilizations. But the merger might also create new opportunities for space travel. The gravitational chaos will fling some stars into highly elliptical orbits that carry them far from the galactic center before returning. A civilization that times its departure correctly could ride such a stellar orbit to explore the outer reaches of the merged galaxy with minimal energy expenditure. It's cosmic surfing on gravitational waves. The study of galaxy mergers has revealed surprising connections to the formation of supermassive black holes themselves. Current theories suggest that the first supermassive black holes formed in the early universe through the direct collapse of massive gas clouds or the growth of smaller seed black holes. Galaxy mergers provide a mechanism for these black holes to grow rapidly by accreting gas and merging with other black holes. The James Webb Space Telescope has already observed supermassive black holes in galaxies less than 1 billion years after the Big Bang, much earlier than previous theories predicted. These observations suggest that black hole growth and galaxy evolution are intimately connected from the very beginning. Our merger with Andromeda continues this ancient dance between galaxies and their central black holes. The chemical evolution during the merger will create a complex archaeological record. Different stellar populations will mix, creating a galaxy with multiple chemical signatures. Red giant stars, which can live for billions of years, will carry chemical fingerprints from their birth environments. By analyzing these stellar fossils, future astronomers will be able to reconstruct the merger history in exquisite detail. The Apogee survey has already demonstrated this technique in our own galaxy. By measuring the chemical compositions of hundreds of thousands of stars, astronomers have identified stellar populations that originated in satellite galaxies consumed by the Milky Way billions of years ago. The merger with Andromeda will add new layers to this chemical palimpsest, creating an even richer record of galactic archaeology. Stellar kinematics, the study of how stars move, provides another tool for understanding merger history. Stars from different progenitor galaxies retain memory of their origins in their orbital properties. The Gaia mission has revealed stellar streams and moving groups throughout the Milky Way, evidence of past mergers and interactions. After the Andromeda collision, the merged galaxy will contain a complex mixture of stellar populations with different kinematic signatures. The role of intermediate mass black holes during the merger adds another layer of complexity. These black holes, with masses between stellar mass and supermassive black holes, might exist in the centers of globular clusters and dwarf galaxies. When these smaller systems are disrupted during the merger, their black holes could be liberated to wander through the galaxy. Some might eventually spiral into the central supermassive black hole, while others could remain as isolated wanderers for billions of years. The search for intermediate mass black holes remains one of astronomy's ongoing challenges. Unlike stellar mass black holes, which can be detected through gravitational waves when they merge, and supermassive black holes, which reveal themselves through their effects on surrounding gas and stars, intermediate mass black holes are notoriously difficult to find. The merger might actually help by disrupting their host systems and making them more detectable. Tidal disruption events will become more common during and after the merger. As the galactic structure becomes more chaotic, stars will be scattered into orbits that bring them close to the central black hole. When a star passes within the tidal radius of a black hole, it's stretched and torn apart by gravitational forces. Half the stellar material falls into the black hole, while the other half is ejected at high speed, creating a brilliant flare that can outshine the entire galaxy. The Zwicky Transient Facility and other survey telescopes detect dozens of tidal disruption events each year in distant galaxies. These events provide unique laboratories for studying black hole physics and the behavior of matter under extreme conditions. Milkymeda's massive central black hole will produce particularly spectacular tidal disruption events, briefly illuminating the merged galaxy across cosmic distances. The merger will also affect the galaxy's rotation curve, the relationship between orbital velocity and distance from the galactic center. Spiral galaxies like the Milky Way and Andromeda have flat rotation curves, meaning stars orbit at roughly constant speeds regardless of their distance from the center. This flat rotation is evidence for dark matter, which provides the additional gravitational force needed to keep outer stars in orbit. Elliptical galaxies have different rotation properties. Instead of organized rotation, their stars follow random, elliptical orbits in all directions. The velocity dispersion, the spread of stellar velocities, increases toward the galactic center, reflecting the deeper gravitational potential well. This transformation from rotation-supported to dispersion-supported dynamics represents a fundamental change in galactic structure. The globular cluster system of the merged galaxy will be a fossil record of the collision. Globular clusters are among the oldest objects in galaxies, with ages approaching the age of the universe itself. They survive galaxy mergers largely intact, though their orbits are dramatically altered. The combined globular cluster system of Milkymeda will contain clusters from both progenitor galaxies, each carrying chemical and kinematic signatures of their origins. Current observations show that the Milky Way has about 150 globular clusters, while Andromeda has roughly 250. The merged galaxy will inherit most of these, creating a system of about 400 globular clusters. This rich population will provide future astronomers with a detailed record of the merger process and the chemical evolution of both progenitor galaxies. The planetary nebula population will also be affected by the merger. Planetary nebulae are the glowing shells of gas ejected by dying sun-like stars. They serve as traces of stellar populations and galactic structure. During the merger, the chaotic gravitational environment will scatter planetary nebulae throughout the galaxy, erasing the organized patterns seen in spiral galaxies today. But the merger will also create new planetary nebulae as the starburst triggers the formation of massive stars that evolve quickly. These stars will live fast and die young, enriching the interstellar medium with heavy elements before exploding as supernovae or ejecting their outer layers as planetary nebulae. The chemical compositions of these nebulae will record the conditions during the merger epoch. The cosmic ray population will undergo dramatic changes during the collision. Cosmic rays are high-energy particles accelerated by supernova shock waves and other violent processes. The increased supernova rate during the merger will boost cosmic ray production, while the tangled magnetic fields will trap these particles more efficiently. The merged galaxy might become a more powerful source of cosmic rays, potentially affecting any planets within its boundaries. High-energy gamma rays produced by cosmic ray interactions will make the merged galaxy brighter in gamma-ray observations. The Fermi Gamma Ray Space Telescope has detected gamma-ray emission from several nearby galaxies, revealing the cosmic ray populations within them. Future gamma-ray observatories will be able to study the cosmic ray enhancement during galaxy mergers, providing insights into particle acceleration in these extreme environments. The merger's impact on stellar evolution will be profound and far-reaching. During the collision, the increased density of stars and gas will create environments unlike anything we see in isolated galaxies today. Close stellar encounters, while still rare, will become more frequent. Binary star systems might be disrupted, creating single stars with unusual properties or new binary pairs with exotic orbital characteristics. The Wolf-Rayet stars, massive, evolved stars that have shed their outer hydrogen layers, will play a particularly dramatic role during the merger. These stellar powerhouses burn helium and heavier elements in their cores while ejecting material at speeds of thousands of kilometers per second. The merger-triggered starburst will create many more Wolf-Rayet stars than normal, filling the galaxy with their powerful stellar winds and preparing for spectacular supernova explosions. When Wolf-Rayet stars explode, they can produce some of the most energetic supernova in the universe. These hypernova events release more energy than typical supernova and might even trigger gamma-ray bursts, the most powerful explosions known. During the peak of the merger starburst, Milky could experience dozens of these extreme events per year, compared to perhaps one every few centuries in a quiet galaxy like our current Milky Way. The neutron star population will also be dramatically affected. Neutron stars are the ultra-dense remnants of massive stars, containing more mass than our Sun, compressed into a sphere just 20 kilometers across. During the merger, the chaotic gravitational environment will alter neutron star orbits, potentially bringing binary neutron star systems closer together and accelerating their eventual merger through gravitational wave emission. Binary neutron star mergers are cosmic gold mines, literally. These collisions produce heavy elements like gold, platinum, and uranium through rapid neutron capture processes that can't occur anywhere else in the universe. The increased rate of neutron star mergers during our galactic collision will enrich Milky with these precious metals, potentially making planets in the merged galaxy richer in heavy elements than those forming today. The Laser Interferometer Gravitational Wave Observatory has already detected several neutron star mergers, including the famous GW170817 event that was observed simultaneously in gravitational waves and electromagnetic radiation. This kilonova explosion was visible for weeks, glowing with the light of newly synthesized heavy elements. During our merger, such events will become much more common, painting the galaxy with the signatures of cosmic alchemy. Magnetars, neutron stars with magnetic fields trillions of times stronger than Earth's, will also be created during the merger. These exotic objects occasionally produce giant flares that release more energy in 1/10 of a second than our Sun produces in a year. The intense magnetic fields can actually affect the structure of space-time itself, creating conditions that exist nowhere else in the universe. A Magnetar flare in the merged galaxy could potentially sterilize planets hundreds of light-years away. The formation of stellar mass black holes will accelerate during the merger as well. The most massive stars born during the Starburst will collapse directly into black holes when their nuclear fuel is exhausted. Some might even form through pair instability supernovae. Explosions so violent they completely destroy stars with masses between 130 and 250 times our Sun's mass. These events haven't been definitively observed in our current galaxy, but could become common during the merger. The population of X-ray binaries will explode during the collision. These systems consist of a compact object, either a neutron star or black hole, accreting material from a companion star. The gravitational energy released as material spirals into the compact object heats the gas to millions of degrees, producing brilliant X-ray emission. During the merger, the disruption of stellar orbits will create many new X-ray binary systems while destroying others. Some X-ray binaries become ultraluminous X-ray sources, or ULXs, that shine brighter than any single star should be able to. These mysterious objects might be intermediate mass black holes, stellar mass black holes accreting at super Eddington rates, or neutron stars with extremely strong magnetic fields. The merger environment will create ideal conditions for forming ULXs, potentially solving the mystery of how these extreme objects form. The interstellar medium, the gas and dust between stars, will undergo complete transformation during the merger. Currently, this material is organized into a complex ecosystem of hot and cold phases with dense molecular clouds where stars form connected by networks of warm, diffuse gas. The collision will heat, compress, and turbulently mix this material, creating conditions unlike anything in the present-day universe. Superbubbles, vast cavities blown out by multiple supernova explosions, will become enormous during the merger. These structures can grow to hundreds of light-years across, filled with million-degree gas that glows brightly in X-rays. The increased supernova rate will create superbubbles that merge and overlap, potentially blowing holes completely through the galactic disk and allowing hot gas to escape into intergalactic space. The dust content of the merged galaxy will initially increase as dying stars inject new dust grains into the interstellar medium. But the intense radiation from young, massive stars will also destroy dust through a process called photodestruction. The balance between dust creation and destruction will determine whether Milky Way becomes dustier or cleaner than its progenitor galaxies. Current observations of galaxy mergers show both outcomes are possible, depending on the specific conditions. Polycyclic aromatic hydrocarbons, or PAHs, are complex carbon molecules that glow brightly in infrared light when excited by stellar radiation. These molecules are thought to be important building blocks for more complex organic chemistry and potentially even life itself. The merger will create, destroy, and redistribute PAHs throughout the galaxy, potentially affecting the chemical conditions for life in ways we're only beginning to understand. The cosmic web, the large-scale structure of dark matter filaments that connects galaxies across the universe, will also be affected by our merger. The local group currently sits at the intersection of several dark matter filaments, which channel gas and smaller galaxies toward us. As Milky Way forms, it will become an even more massive node in this cosmic web, potentially attracting additional material from intergalactic space. This continued accretion could extend the merger process far beyond the initial collision. Small galaxies and gas clouds flowing along dark matter filaments might continue falling into Milky for billions of years after the main merger completes. Each new addition will trigger smaller starbursts and add to the galaxy's mass, gradually building an even more massive elliptical galaxy. The local void, a region of space near us that contains unusually few galaxies, will influence the merger's long-term evolution. Voids in the cosmic web are expanding faster than average due to their low density, creating outflows that can strip gas from nearby galaxies. As cosmic expansion accelerates, the local void will grow larger and might eventually begin affecting Milky's ability to retain its outer gas halo. The merger will also create a new population of intracluster light, stars that don't belong to any particular galaxy, but instead orbit in the gravitational potential of the entire system. During the chaotic collision process, some stars will be stripped from their parent galaxies and scattered into the space between them. These orphaned stars will create a faint, diffuse glow that extends far beyond the visible boundaries of Milky. Current observations of galaxy clusters show that intracluster light can contain up to 50% of the total stellar mass in the most massive systems. While our local group is much smaller than a galaxy cluster, the merger will still create a significant population of these homeless stars. Future observations might detect this intracluster light as a faint halo surrounding the merged galaxy. The gravitational microlensing rate will change dramatically during the merger. Microlensing occurs when a foreground object, usually a star or planet, passes in front of a background star, temporarily brightening it through gravitational focusing. The chaotic stellar motions during the merger will create new microlensing opportunities while destroying others. This could affect our ability to detect planets around distant stars using this technique. Surveys like the optical gravitational lensing experiment and the microlensing observations in astrophysics project currently monitor millions of stars for microlensing events. During the merger, the rate and characteristics of these events will change as stellar orbits become more random and eccentric. This could actually improve our ability to detect free-floating planets, worlds ejected from their star systems during the gravitational chaos. The merger will affect the galaxy's ability to form new planetary systems. The increased metallicity from supernova enrichment will provide more raw materials for planet formation, potentially creating super-Earths and gas giants with compositions unlike anything in our current solar system. But the intense radiation environment and frequent stellar encounters might also disrupt planet formation or strip atmospheres from newly formed worlds. Hot Jupiters, gas giant planets orbiting very close to their stars, might become more common during the merger. These exotic worlds are thought to form farther from their stars and then migrate inward through gravitational interactions with other planets or the protoplanetary disk. The chaotic environment during the merger could trigger more of these migration events, creating planetary systems with architectures very different from our own. The habitability of planets in the merged galaxy will depend on many factors. The increased supernova rate will create more frequent sterilization events, but it will also enrich the interstellar medium with elements essential for life. The disruption of stellar orbits might move some planets into more favorable locations, while ejecting others into interstellar space. Overall, the merger might actually increase the number of potentially habitable worlds, even as it makes individual planets less likely to maintain stable conditions for long periods. Rogue planets, worlds ejected from their star systems, will become much more common during the merger. Current estimates suggest there might already be billions of rogue planets wandering through our galaxy, invisible except when they occasionally pass in front of background stars. The gravitational chaos of the merger will create many more of these orphaned worlds, some of which might retain internal heat to support subsurface oceans and potentially even life. The Nancy Grace Roman Space Telescope, scheduled for launch in the mid-2020s, will conduct the first comprehensive survey of rogue planets in our galaxy. By the time of the merger, similar surveys might reveal a vast population of these wandering worlds, creating a new category of potentially habitable environments that don't depend on stellar radiation for energy. The merger will also affect the galaxy's magnetic field structure on the largest scales. Both the Milky Way and Andromeda possess complex magnetic fields that thread through their spiral arms and extend into their halos. When these fields interact during the collision, they'll create regions of enhanced magnetic field strength that could affect cosmic ray propagation and star formation for billions of years. Magnetic reconnection events, sudden releases of magnetic energy similar to solar flares but on galactic scales, might occur during the merger. These events could accelerate particles to extreme energies and produce bursts of high-energy radiation detectable across cosmic distances. The merged galaxy might briefly become one of the most powerful sources of cosmic rays and gamma rays in the local universe. The study of galactic magnetic fields remains one of the frontiers of astronomy. Radio telescopes can map these fields by observing polarized emission from cosmic ray electrons, but the techniques are still being refined. Future radio arrays, like the Square Kilometre Array, will provide unprecedented views of magnetic field evolution during galaxy mergers, potentially revealing new physics about how magnetic fields behave in extreme environments. The formation of new star clusters during the merger will create some of the most spectacular stellar nurseries in the universe. When gas clouds collide at hundreds of kilometers per second, they compress and fragment into dense cores that collapse to form stars. But unlike the relatively gentle star formation we see today, merger-triggered starbursts create massive stellar associations containing millions of young stars packed into regions just a few light-years across. These superstar clusters will be visible as brilliant blue knots throughout the merging galaxies, each one containing more stars than the entire Orion Nebula region. The most massive clusters might even survive the merger to become new, globular clusters, adding to the fossil record of this cosmic collision. Current observations of the antennae galaxies show dozens of these young superclusters forming in real time, providing a preview of what awaits our own galactic neighborhood. The Hubble Space Telescope has revealed that some merger-triggered star clusters contain stars with masses exceeding 150 times our Sun, far more massive than any stars forming in our galaxy today. These stellar giants burn through their nuclear fuel in just a few million years before exploding as pair instability supernovae, events so violent they completely destroy the star and leave no remnant behind. The energy released by just one of these explosions exceeds that of a typical supernova by factors of 10 to 100. The chemical signatures of pair instability supernova are distinctive, producing unusual ratios of elements that serve as fingerprints of these extreme events. Future stellar archaeologists studying the merged galaxy will be able to identify stars that formed during the merger epoch by looking for these chemical signatures in their spectra. It's like having a cosmic timestamp written in the very atoms that make up each star. The merger will also trigger the formation of luminous blue variables, massive, unstable stars that undergo dramatic eruptions throughout their lives. Eta Carinae in our galaxy is the most famous example, having ejected several solar masses of material during a giant outburst in the 1840s. During the merger starburst, dozens of these stellar time bombs will pepper the galaxy, each one capable of erupting with the brightness of an entire galaxy for months or years at a time. These stellar eruptions will enrich the interstellar medium with processed material from stellar cores, including elements like nitrogen and fluorine that are difficult to produce through other mechanisms. The merger epoch will be a time of rapid chemical evolution, with the galaxy's metallicity increasing dramatically over just a few 100 million years. This chemical enrichment will affect every subsequent generation of stars and planets. The formation of Wolf-Rayet stars will reach unprecedented levels during the merger. These evolved massive stars have shed their hydrogen envelopes, revealing cores burning helium and heavier elements at temperatures exceeding 100 million Kelvin. Their powerful stellar winds, moving at speeds up to 5,000 kilometers per second, will carve enormous cavities in the surrounding gas and trigger the formation of new stars through compression of nearby molecular clouds. The collision between stellar winds from different Wolf-Rayet stars will create spectacular, shock-heated bubbles visible in X-ray observations. These wind-wind collision zones can accelerate particles to relativistic speeds, potentially contributing to the galaxy's cosmic ray population. The merged galaxy will become a cosmic particle accelerator on scales we can barely imagine. Brown dwarfs, failed stars with masses too low to sustain nuclear fusion, will also be affected by the merger. These objects, sometimes called stellar embryos, form when gas clouds fragment but don't accumulate enough mass to ignite hydrogen burning. During the chaotic merger environment, some brown dwarfs might accrete additional material and cross the threshold to become true stars. Others might be ejected from their birth clusters to wander the galaxy as isolated substellar objects. The population of free-floating brown dwarfs will increase dramatically during the merger as stellar encounters disrupt young clusters and scatter their lowest mass members. These orphaned objects will be nearly impossible to detect directly but might occasionally reveal themselves through gravitational microlensing events or infrared emission from their slowly cooling surfaces. The merger will create ideal conditions for forming intermediate mass black holes through runaway stellar collisions in dense star clusters. When thousands of massive stars are packed into a small volume, they can undergo a cascade of collisions that builds up a single, extremely massive star. This monster star, potentially weighing hundreds of solar masses, would quickly collapse into an intermediate mass black hole. These intermediate mass black holes have been notoriously difficult to find in the current universe, but the merger environment might produce dozens or even hundreds of them. Some will eventually spiral into the galactic center and merge with the supermassive black hole, while others might remain in the outer regions of the galaxy as wandering gravitational monsters. Future gravitational wave detectors will be able to track these objects as they occasionally capture and disrupt passing stars. The X-ray emission from the merged galaxy will be dominated by these various high-energy processes. Hot gas heated by supernova shocks will glow at temperatures of tens of millions of degrees. Accretion onto black holes and neutron stars will create point sources that can outshine entire star clusters. The overall X-ray luminosity of Milky Way might increase by factors of hundreds during the peak merger phase. The Chandra X-ray Observatory and XMM Newton have observed similar X-ray enhancement in other galaxy mergers, revealing the violent processes occurring during these cosmic collisions. Future X-ray missions with improved sensitivity and spatial resolution will be able to study individual sources within merging galaxies, providing detailed insights into the physics of extreme stellar environments. The radio emission from the merged galaxy will also be dramatically enhanced. Supernova remnants will accelerate cosmic ray electrons that emit synchrotron radiation as they spiral around magnetic field lines. The increased supernova rate during the merger will create a population of young, bright supernova remnants that make the galaxy shine brightly at radio wavelengths. Pulsar formation will accelerate during the merger as massive stars collapse into rapidly spinning neutron stars. These cosmic lighthouses emit beams of radio waves that sweep across space like lighthouse beams. The merged galaxy might contain hundreds of thousands of active pulsars, compared to the roughly 3,000 known in our current galaxy. This pulsar population will provide unprecedented opportunities for studying neutron star physics and testing theories of gravity in extreme environments. Some pulsars formed during the merger might have unusual properties due to the chaotic formation environment. Magnetars, neutron stars with magnetic fields quadrillions of times stronger than Earth's, might be more common if the merger triggers the formation of highly magnetized massive stars. These objects occasionally produce giant flares that release more energy in seconds than our Sun produces in years. The merger will also affect the galaxy's population of stellar remnants in more subtle ways. White dwarf stars, the cooling cores of Sun-like stars, will be scattered into new orbits by gravitational encounters. Some white dwarfs in binary systems might begin accreting material from their companions at accelerated rates, potentially triggering Type Ia supernovae that serve as standard candles for measuring cosmic distances. The rate of Type Ia supernovae will increase during the merger as stellar encounters disrupt binary systems and bring white dwarfs closer to their companions. These explosions are crucial for enriching the galaxy with iron peak elements like iron, nickel, and cobalt. The merger epoch will see a dramatic increase in the production of these elements, affecting the composition of all subsequent stellar generations. Planetary nebulae, the glowing shells ejected by dying sun-like stars, will also be affected by the merger. The chaotic gravitational environment will distort these delicate structures, creating asymmetric shapes and complex morphologies. Some planetary nebulae might be completely disrupted, while others could be compressed and brightened by shock waves from nearby supernova explosions. The central white dwarf stars of planetary nebulae will be scattered throughout the merged galaxy, carrying with them the chemical signatures of their progenitor stars. These stellar fossils will provide future astronomers with detailed records of stellar evolution during the merger epoch, preserving information about stellar masses, metallicities, and formation environments. The merger will create a new class of stellar streams, long, thin trails of stars torn from disrupted clusters and associations. Unlike the relatively simple streams we see today from disrupted satellite galaxies, merger-induced streams will have complex braided structures reflecting the chaotic gravitational environment. These streams will persist for billions of years after the merger, serving as fossil evidence of the collision. The Gaia mission has already revealed numerous stellar streams in our galaxy, including some that wrap around the Milky Way multiple times like cosmic ribbons. During the merger, these existing streams will be disrupted and new ones created, writing a complex history in the positions and motions of stars. Future astrometric missions with even greater precision will be able to untangle this stellar archaeology and reconstruct the merger process in unprecedented detail. Hypervelocity stars, objects moving fast enough to escape the galaxy entirely, will be produced in large numbers during the merger. The gravitational slingshot effect from close encounters with massive objects can accelerate stars to speeds exceeding 1,000 kilometers per second. Some of these stellar refugees will carry planets with them into intergalactic space, creating isolated planetary systems drifting through the cosmic void. The discovery of hypervelocity stars has already provided insights into the structure and mass of our galaxy. During the merger, the production rate of these stellar outcasts will increase dramatically, potentially creating a population of intergalactic wanderers that carry information about the collision to distant parts of the universe. Future surveys might detect these stellar messengers in nearby galaxy groups, providing direct evidence of our ancient merger. The merger will also affect the galaxy's ability to retain its gas content. The combined gravitational potential of Milky will be deeper than either progenitor galaxy, making it harder for gas to escape. But the intense stellar feedback during the starburst phase will drive powerful galactic winds that can blow gas completely out of the galaxy. The balance between these competing effects will determine whether the merged galaxy becomes gas-rich or gas-poor. Observations of other galaxy mergers show both outcomes are possible. Some merged galaxies retain significant gas reservoirs and continue forming stars for billions of years after the collision. Others are stripped of their gas and become red and dead ellipticals with little ongoing star formation. The fate of Milky will depend on the specific details of the merger process and the efficiency of stellar feedback. The cosmic ray population will undergo dramatic changes during the collision. These high-energy particles, accelerated by supernova shockwaves and other violent processes, will be trapped more efficiently by the tangled magnetic fields created during the merger. The galaxy might become a more powerful source of cosmic rays, potentially affecting the habitability of planets throughout the system. High-energy gamma rays produced by cosmic ray interactions will make the merged galaxy visible to gamma-ray telescopes across cosmic distances. The Fermi Gamma Ray Space Telescope has already detected several nearby galaxies in gamma rays, revealing their cosmic ray populations. During the merger, this gamma-ray emission will increase dramatically, creating a beacon visible throughout the local group and beyond. If you are still watching, make sure to subscribe to the channel and turn on the notification bell. And check out this other video at the left side of the screen. Is the speed of light really the fastest thing in the universe? In this video, we explore the science behind the speed of light limit, from superluminal jets and quantum entanglement to cosmic inflation, wormholes, and the mysteries of dark energy. It's a must-watch.